Okay, kids, we're back, and today we want to talk about a type of magnetism called electromagnetism. Electromagnetism. Now, I hope you watched that second segment of the video first before you're listening to this video lesson. It'll be a lot easier for you. So, what is electromagnetism? Well, it's a magnetic field, B arrow, symbol for magnetic field, that is created by an electric current in a conductor. So we really need to investigate electric current because there's two ways of thinking about electric current. Electric current can be thought of as electron flow, the physical movement of electrons through a wire as they leave the negative end of a power supply, go into the circuit, and then back to the positive end. That's electron flow. And when you study electron flow, you use the left-hand rule that you saw in the video for deciding what is the direction and shape of the magnetic field. But left-hand rule and electron flow are a physical model of what is occurring. We've talked about this issue before. If you want to look at this mathematically, and this is really important if you choose to go on to the 4U physics, you have to consider positive conventional current. I. You've seen the symbol for current before. It doesn't flow from negative to positive. It's the opposite. It flows from positive to negative. Opposite direction to electron flow. If we are going to use that, and we are going to use it because your textbook uses it, we will use the right-hand rule to establish the direction and shape of magnetic fields created by uh, the movement of charges within a wire or the movement of charges within a coil solenoid. So please be aware of this. The video is all about left-hand rule because it's using electron flow. Our textbook and most textbooks and most textbooks around the world, and the majority way of looking at this is through positive conventional current right-hand rule. So please be aware of that. So we're using uh, electric current here. This is positive conventional current. This is I. It's not electron flow. And we're using our right hand. If you have a straight wire like this, straight conductor, just a wire like that, and the current moves from left to right, just like that. In order to find the direction of the magnetic field that is created, you need to establish a pattern where you align your thumb with the direction of the current and your fingertips curl as if they're holding a handlebar upside down in this particular case. Okay. So look at your fingertips. Your fingertips are showing you the direction of the circular magnetic field that exists around the wire. So look at these fingertips here. Look at the direction in here. They match this direction right here. And the shape of the magnetic field, as you saw in the video, is a set of circles with the same center, the center being where the electric current is. So they are called concentric circles. Con with center with the same center circles, concentric circles. So here's the magnetic field line around this wire when there's an electric current going through it, and we get the direction of the magnetic field from our right-hand rule. So you've got to remember, this is magnetic field right here. Magnetic field, look at the symbol for magnetic field, B arrow hat. It's a vector. I need a way of finding the direction. The right-hand rule provides that for us. Now, sometimes they'll show you a wire. Here's the wire, and you're looking straight on the end of the wire, and you'll see an X. When you see an X like that, it's telling you, look, this is a wire, and the current is going into the page. The X means into the page. So you've got to get your thumb and point it into the page, or in this case, point it into the computer screen. And if you take a look at your thumb, now you're using your right hand, your thumb is pointing right into the screen because that's the direction of the current. And look at the direction of your fingertips curling, right? Your fingertips are going to curl, so this is a clockwise direction. Next, if you see this symbol right here, this is telling you, hey, there's a wire that's going in and out of the page, a wire that's going in and out of the screen. You're looking at the wire head on. But now there's a dot here. So that dot is telling you that the current is coming out of the page, out of the computer screen. So you have to align your thumb to point out of the page, out of the computer screen. And now look at your fingertips curling now, right? They curl in the other direction. This would be counterclockwise curling or direction. All right? And the other thing they're showing here is look how close these magnetic field lines are. They're quite close to each other. Look how close these are, further apart. Because the further you get away from the source of the magnetic field, that's the current in the wire, the weaker the magnetic field is. So stronger gets magnetic field gets weaker, 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 weaker as you get farther away from the source. The other thing you need to realize is as soon as you turn off the current, bingo bango, there's no more magnetic field. It's magic. Well, not really. It's physics. That's it. It's not the wire itself. It's the fact that there's a current in the wire that there's a magnetic field. Remember what type of magnetism we're studying here? Electromagnetism. You have to have an electric current in order for there to be a magnetic field. So here's just a quick little handwritten note. B, magnetic field, all right, around a straight conductor known as a wire. So here's the wire. There's the current for it. So I've shown you a textbook version of this. Here is the wire with the current coming out, and the magnetic field around it would be a bunch of circles, concentric circles around it. Here is a wire with the current going in to the page, and I haven't drawn very good circles here, but it's circles like this all around it. And we use the right hand rule for straight conductors to figure out the direction of this current, of the magnetic field. I beg your pardon. So let's read what it says here. The magnetic field weakens. Magnetic field weakens further from the current. So the further you get away from the wire, the weaker the magnetic field. The right-hand rule for conductors says the following. Point your thumb in the direction of the current, right? An open hand curls with the fingertips pointing in the direction of the magnetic field. That's what we learned there. Now, the other very important configuration for a conductor is a coil or solenoid. Now look, this is the current, I. So the current is going up here, right? Look, follow it. It's going down behind it and then up in front. Then let's follow this. Down behind it, up in front. Down behind it, you see the wire back there? Up in front. So that means all the wires at the front of the coil, the part of the coil that's facing you, the current is moving upward here. So at the front of the coil, the current is moving upward. Then what happens to the current? Well, then at the very top, the current goes into the page, right? At the very top, the current goes into the page because the coil is twisting there, or it's finishing off its circle. Then way back here, you can see them kind of back in the distance. These ones that are hidden behind here, back there, the current is, look, coming downward. So way back in here, I don't want to confuse this too much, but back there, in the part of the coils that are on the other side here, the current is going down. Then along the bottom here, the current is coming out towards you. Well, we want to understand the type of magnetic field that is created here. Well, the magnetic field looks like what they've drawn here. It's pretty constant. Take a look at this. This is the magnetic field inside a coil. It's pretty constant, runs all the way through. Look at these magnetic field lines. Pretty constant, runs all the way through. Now, are there some weaker magnetic fields that kind of sneak outside? Yes, there are. They're quite weak. They're not as strong as the magnetic field inside the coil. But right, it's magnetic field. It's a vector. I need to figure out the direction here. This is the shape of it, great. But I need to figure out the direction of it. And the way you do that is you get your right hand out. You get your right hand out and you try to curl your fingertips. So you're going to try to curl your fingertips so that it matches up with these arrows here. So it matches up with going up, into, down in the back, and at the bottom coming back out. So you want this to really match the direction of the current. So you want your fingertips to match with what is happening with the current here, which is up in front, into the page at the top, down in the back, and towards the front in the bottom. You want to match this with your fingertips. When you match that curling direction of the current in the coil, look where your thumb points. Your thumb is pointing that way. And that way means this is where you place the north seeking pole. And then by default, the south seeking pole is here. So this is a right-hand rule for coils. And you get your fingertips to match the curling current. Now let's take a look at the magnetic field in a coil. Here's a coil. And here is a bar magnet. Look how similar the magnetic fields are. Very similar. Okay. This is created through what we learned a few days ago. Remember, we called this ferromagnetism. Remember, we had a little history lesson about how they found this in magnesia, all right, with the lodestone. And here is a current. So remember what current means. It leaves the positive and goes into the negative. Long line positive, short line negative. And then look what happens. The current, look what it does. It goes up in front, into the page, down behind. Then at the bottom, it comes back out towards you. Then up in front, into the page, down behind, then comes back towards you. And you can finish this pattern out all the time. Then you've got to get your right hand to curl like that. Get your right hand to go up in front. At the top, go into the page. Then behind the coil, your fingertips will curl down. Then at the bottom of the coil, your fingertips will curl towards you. That's the direction of the curling you want. You want your fingertips to match the flow of current. And look where your thumb is. Your thumb is pointing to the left. And that's where you will put the north-seeking pole. And by default, you got the south-seeking pole here. So let me do an example for you from scratch so you have an understanding here. So what do we have here? We've got some type of power supply. We've got a coil and we've got a compass here and a compass here. Compasses are tiny magnets which are allowed to spin on somehow some magnetism. Some mechanism lets them spin, like a tiny magnet that would be pivoting on a sharp pin, for example. What would I do first here? Well, I would establish long line positive, short line negative for this power supply. Then I would establish that current leaves the positive and current enters the negative. And I would follow that direction. Okay, I got to follow this direction. Here goes. Oh, now it's up behind. I don't see the wire. Then the current comes back towards me, then down in front. Then the curl goes into the page. Up behind, towards me, down in front. Down in front, then into the page, and the process continues. So this is the direction of the current. So now what you do, you got to get your right hand out, and your right hand, it's got to have its fingertips curl with the direction of the current as it moves in a coil. So the direction is the current goes up behind in the parts of the windings you don't see. Then at the top, the current is coming towards you. Then the parts of the windings that you do see in the front is down, right? And then at the bottom, the current goes into the page. So if you curl like that, I hope you're getting your thumb is pointing right there. And that means this is where the north-seeking pole is. Your thumb is pointing to the right. So that's where you would put the north-seeking pole. And then by default, the south-seeking pole is right there. The next thing you got to remember is that magnetic field lines, right, are very similar to that of a bar magnet. So we kind of draw it as best we can, right? Kind of looks like the magnetic field of a bar magnet. All right, might have some sneaking out here, some sneaking out. I don't want to complicate my drawing too much. The other thing you got to realize is magnetic field lines always leave the north. So there's my arrow. Magnetic field lines leave the north. Look at this one. Leaves the north. Magnetic field line leaves the north. And then magnetic field lines enter the south-seeking pole. Look at my arrows. The magnetic field line enters the south-seeking pole. Well, a compass a compass will point in the direction of the magnetic field. So a compass would align itself with that magnetic field line. The compass would align itself with the magnetic field line. That's how you would do this one. Now here's another way of looking at this. Instead of drawing the wires and the power supply, this is a cross-section view. So this is a coil, but it's a cross section. So here are the wires at the top of the coil. Here are the wires at the bottom of the coil. They don't show the entire wires in front and behind. They're just showing you the direction of the current at the top and the direction of the current at the bottom. So at the top, the current is out. At the bottom, the current is in. So now you've got to get your fingertips to curl like that. So they got to go at the top, they've got to go out, and at the bottom, your fingertips have got to point by going in. So the only way I can do that, have my fingertips go out towards me at the top, out of the page at the top, then curl down, and then at the bottom, I can twist them to curl into the page. The only way I can do that with my right hand, it has to be your right hand, is if my thumb points to the right, right? So if my thumb points to the right, that means this is where the north-seeking pole is on the right. And this is where the south-seeking pole is by default on the other side. And then we're going to draw magnetic field lines. And magnetic field lines for a coil are very much like the magnetic field line of a bar magnet. Kind of looks like this. I don't want to overcomplicate my drawing here. All right, kind of looks like this. All right. The other thing you have to remember is magnetic field lines always leave the north. Magnetic field lines leave the north-seeking pole. Magnetic field lines go into the south-seeking pole. They always do that. And then you got these compasses here. Well, compasses align themselves with the magnetic field line where they are. So that's what the compass would be, just like that. All right. So that's what I have here in the note, that the magnetic field of a coil or a solenoid looks like the magnetic field of a bar magnet. We have to use the right hand rule with the fingertips curling in the direction of the current, and that's what I have here. And the thumb points in the direction of the magnetic field, and that's what I have here. So your thumb is going to point to where the north-seeking pole is. And it's a magnetic field shape that's very similar to a bar magnet. And I've done nicer demonstrations of this a few moments ago in the previous part of this lesson as opposed to this drawing part. I used a textbook picture that's a little bit clearer. So make sure you use your right hand. Tire it out. That's the only way you're going to learn. Have a great day. Bye bye.